amount to syntactical sugar. Like passing by reference in C++ really is just passing a pointer and dereferencing it. But under the hood, how much do you, the programmer, have to type in that makes all the difference?
Your question? Yes. You're not like looking so she'll have
Archiving. Okay. We should be good to go. All right. So apparently multiple people thought I was only kidding when I said we were going to have class today. Well, we have a few extra participants via WIMBA. I should give those people who are supposed to be in class an in-class exam. Stephen and Jake are dying of a heart attack right now. Okay, anyway, so, questions? Oh, yeah, it has to compile. Your problem from the book, yes, has to compile. You should supply macro definitions along with a program that instantiates them. If you have more than one .c file, I want to make file. But if you submit just one .c file, you can have a separate header file, but if you just have one source file, just submit the source file. But yeah, it's got to compile. Mitch.
In the book, it has a list of macros that they said you should define, one of them being others in all caps. But then when he shows an example code, he says when others. Can we just do others and not have our when have to handle the others?
Okay, so do we really have to make a macro out of others? Yes, you do have to follow the convention of the book. Others should be a separate macro from when, and it should be a parameter so you have to instantiate it with when, parenthesis, others, close parenthesis. So it should just expand to a particular parameter you pass to the when macro.
Another question. The others is supposed to raise the exception in the surrounding exception domain.
Mm-hmm. So when others does not necessarily raise the exception in the surrounding domain. When others, what that does is it just is your default. It's your catch ...
So, because one of the comments in that says something about raising the exception.
So in Ada, you would typically raise the exception in the surrounding domain. But since you don't have a surrounding domain, you don't have to raise the exception in the surrounding domain. This is just your default handler.
So to raise an exception in the surrounding domain, would you just keep passing on like if there was an exception, you just pass it on to the rest of
So if you were going to raise the exception in the surrounding domain, you would have to syntactically be able to access the jump buff from the surrounding domain set jump. And that's kind of clunky. So that's where kind of our C to Ada abstraction kind of breaks down, because we don't provide for having multiple jump buffs. We could. Yeah, I think we'll hold off until an exam on that one. Other questions? Okay. Macro homework assignment is due today. Lab 5 is due Tuesday. Lab 5 isn't nearly as tough as Lab 4, so it should be a nice way to recover from the pain of Lab 4. Lab 6 is the material that we're talking about today, and last time, context switching. And we'll also get into the code that we're going to be writing, which is process creation. This is good stuff. So anyway, today we continue on with hardest lecture ever, which is more assembly code in ARM, sorting through, so we've sorted through context switching, which is the code that you're seeing here. Denise, I hope you had a chance to review some of this stuff because we're diving into the middle and you're going to be completely lost. So anyway, my apologies in advance. But we've got the context switch code. We've talked about it twice now. The previous version, which didn't work for preemptive context switching and mixed cooperative and preemptive. This version is set up now to be able to work with cooperative and preemptive context switching. But if we're doing preemptive context switching, we're calling this from an interrupt service routine. And because we're calling it from an interrupt service routine, it's designed to work in conjunction with the ISR's code. That ISR's code, remember, is the first assembly code that gets executed that actually pushes all the registers so that we don't whack the interrupted program's context when we handle an interrupt. And that code, and you have to keep straight in your head, sometimes interrupts happen and they don't have anything to do with a context switch. Sometimes an interrupt happens and it leads to a context switch. So the ISR's code runs every time an interrupt happens, and some of those interrupts lead to a context switch. Okay? So what we have to do is set things up so that we don't kill the program that got interrupted when we cause it to context switch. And we also want to make sure that we preserve the context of the program that we're interrupting for those situations where we don't switch context, but we do handle an interrupt. So in the ISR's code, we still have to push all the registers and save the state of the process so that we don't kill it by virtue of handling an interrupt. There are some extra considerations we have to address because sometimes an interrupt can lead to a context switch. And we have to deal with this mode switching business. Okay? So we've got all of that. And if you remember, we build the stack of the process that we're swapping out. Where it ends up looking like this, where the old process, this is inside our context switch. We've got a bunch of other stuff on the stack. We push all the registers, we push the CPSR, and then at the top of the stack, we push a pointer to the stack. Okay? So we've got at the top of the stack a pointer to itself. Okay? And we decided that if we're doing a cooperative swap in and a cooperative swap out, this doesn't help. It doesn't hurt, but it doesn't help. We put it on there, and then we take it back off without doing anything with it. In the case of a preemptive context switch, we have to have that pointer there because of the fact we need to be able to manage the fact that we're dealing with two stacks, the IRQ stack and the SVC stack. So what we're going to do now is, in the case of an interrupt, we want to look at what does the stack look like before we start handling the interrupt by jumping to the code that's in that accesses the VIC. So this ISR's code that I'm going to show you, if you remember before, what it was is we're just pushing all the registers, jumping to the VIC code that handles the interrupt, and then popping all the registers. Now that code is expanded to the following. So you see all these instructions? That's the first half. Okay? The other half does the same thing that the first half does, but backwards. So it's become big, nice, and nasty. And this is worse than the context switch code, but it is, the whole point is to be able to allow this code to work in conjunction with the context switch so we can support preemptive context switching. So we're going to go through these guys line by line. I've doled this thing out into different steps, and we'll talk about each step individually. And then part of Lab 5, no, actually part of Lab 6, is you get to draw the stack frame. Hope you enjoy. Okay. All right, so again, this is not context switch code. This is handling an interrupt code. And this could possibly lead to a context switch. So we've got a process that's running, or program something, code that's running, and all of a sudden an interrupt happens. Then this code starts to run. What do we do first? The first thing that we do in this code is the thing that we used to do last. Okay? So the first thing we do is we subtract from into R14 4 from R14. So we take R14, subtract 4 from it, and put that into R14. What register is R14? or 15cc? LR, link register. Which link register is it? How many link registers do we have? How many stack pointer registers do we have? We have lots, but we're only worried about two of them, the SVC stack pointer register and the IRQ mode stack pointer register. How many link registers are there? Is this a banked register? Okay. What is the mode of the processor when we start handling an interrupt? When we start at this assembly code? We do know. So if you remember what happens when we get to this ISR's code, this assembly code, what happened is an interrupt source has indicated an interrupt needs to fire. Okay? That interrupt source tells the VIC hardware on the EP9302 chip there's an interrupt that needs to fire. The VIC hardware says, okay, let me assert the IRQ signal. That IRQ signal interfaces to the ARM core. The ARM core reacts saying, oh, there's an interrupt that needs to happen. And it halts the execution of the current instructions that are in the pipeline, lets those that are far enough in finish, and cancels those that aren't far enough in. So, and then it will, it'll take the program counter, which is pointing to the next instruction to execute. It'll take that address and it'll put it into a link register. Okay, that's how it remembers where I'm supposed to go back to. It'll convert the mode of the processor to IRQ mode, and then it'll execute the instruction that's at 0x18. Remember we talked about this a while back? So it goes to the hardware address at 0x18, and at that location we put the binary equivalent of an instruction that says go to address 38 and jump to the address that you find there. Okay, and at that address is the address of the ISR's code. Okay, so the hardware puts us in IRQ mode before we start this assembly code. So the hardware has already put us in IRQ mode. What we said is that the return address for where we're going to return to after we're done is put into a link register. Which link register do you suppose it's put into? If we put it into the SVC mode link register, so the link register is banked, if we put it into the SVC mode link register, well, what happens if we interrupt the program right before it's going to do a return? The return instruction takes the address that's out of the link register and puts it into the PC, and that causes us to go back to wherever the procedure that the interrupted code was running. Well, if the hardware takes the return address from the interrupt and puts it into the SVC mode link register, we've just whacked the SVC mode link register. Well, you say, well, don't we push all the registers? Well, that happens before we get to the code that pushes all the registers. So the hardware can't modify the SVC mode link register. So what it does is it converts us to IRQ mode, and it puts the return address from the interrupt into the IRQ mode link register. Okay? IRQ mode link register is R14. We're accessing the IRQ mode R14 here because of the fact that the processor is in IRQ mode. Okay? Again, similar to stack pointing. You can't tell by looking at the code which mode you're in. You just have to know. Okay? You can explicitly change the mode and keep track of it in that way. But we know that this is code that's getting executed in response to an interrupt, and the processor is already in IRQ mode. So this guy is the IRQ mode link register. We're subtracting 4 from it. Why are we subtracting 4 from it? By virtue of the fact that the processor was executing instructions before it got interrupted, the program counter gets 1 ahead of where it needs to be. We cancel the instruction that it's currently fetching. The program counter is 1 advanced from where it needs to be, so we need to back it up 1 so that it will execute on the return from the interrupt the instruction that got canceled. So we're going to back up the link address by 4 because all the instructions are 4 bytes. So we back it up 1 slot. This is the same thing that we've been doing before. So we adjust the ISR return address by 4. That was one thing that we used to do last in the previous ISRs. We're doing it first now. Why? Because it works better this way. Okay. Next thing we're going to do, we're going to store R0 at SP. We're going to push R0 and push R1. Okay. Why are we pushing R0 and pushing R1? First off, let me ask you, which SP is that? IRQ mode SP or SVC mode SP? IRQ. We are in the interrupt handling code. The processor is already in IRQ mode, so SP refers to the IRQ mode stack pointer. So we're pushing R0 and R1 to the IRQ mode stack. Recall, the IRQ mode stack is shared by all the processes, okay? We use it as a temporary shared scratchpad location where we can put stuff on there, but we can't let stuff sit there across a context switch. So if the process that is being interrupted is eventually going to be preempted or swapped out, how do we know it'll be swapped out? Well, this code's going to call a handler. That code will call a scheduler. The scheduler will decide whether or not this process gets to be swapped out. It may get swapped out. If it does, we can use the IRQ mode stack for a temporary holding location, but we can't let data sit there from one invocation of a process to the next. So we can push stuff on it, but we got to pop stuff back off of it before we context switch. This is because we might swap ourselves out, and we never know how long it's going to be until we swap ourselves back in order to clean up the stuff that we push on. So you push stuff on, but you have to pop it back off before you can do something that could eventually cause you to get swapped out. So what this means is we can push stuff on while we're handling here, but before we get down to the end of the ISR's code where we branch to the interrupt handler, we have to pop up and clean up that IRQ mode stack because we got to leave it in the same state that it is because some other process may need it because all the processes share the same IRQ stack. We have to leave it in the state that it was at before we get swapped out. So, in order to do that, what we need to do is, in this ISR's code, our goal is to save the state of the process, but we don't want to save it as we were doing before onto the IRQ mode stack. We want to save it onto the SVC mode stack of the process because every process has its own stack. In order to do this, we're going to have to mode switch a little bit. And we're going to have to shuffle some pointers around. In order to do that, we need to have the ability to store some addresses in some registers. We need some working space. So we're going to push R0 and R1 to give us a couple of registers to work with. Okay? So we have to push them first because they've got values in them that the interrupted process was using. So we're saving those, and then we're going to save those on the stack. We'll use R0 and R1 to help us save the state of the processor in preparation for handling the interrupt. And then we'll restore them and copy their state onto the SVC mode stack so that we can save them as part of the process's context. So push R0 and R1 in preparation for saving the state. Next, on 3 here. This looks like similar code to what we saw before. We're going to copy the CPSR into R1. We're going to OR R1 with the value 0x01 and move that into CPSR_C. What this does is it changes the mode of the processor to SVC mode. Okay? We were in IRQ mode. We know that we were in IRQ mode, as opposed to the context switch code where we weren't sure what mode we were in, and we just say, change to SVC mode. I don't care if I'm already in there. I know that I'm not in SVC mode here. I know that after here I am in SVC mode. Okay? So I changed to SVC mode. Okay? Why are we changing to SVC mode? Because I'm going to push all the registers in preparation for handling an interrupt, but I don't want to push them onto the IRQ stack. I want to push them onto the SVC stack because that's the process's local stack. That's how we stay independent of all the other processes. So in order to get to the SVC mode stack, I need to find the top of the SVC mode stack. The only way to do that is to access SP, but while in SVC mode. So I change to SVC mode in order to access the top of the SVC mode stack. So 4 executes while we are in supervisor mode. Okay? So what I do is I store LR into SP minus 4 bang. So this pushes LR. Which LR is this? What mode am I in? I just changed the supervisor mode. So this is the supervisor mode link register. I know I need to install updates. Stop yelling at me. Okay. Supervisor mode link register, supervisor mode stack pointer. So I'm pushing the link register of supervisor mode onto the supervisor mode stack. Why am I doing this? Why didn't I have to change to the supervisor mode before? Well, if you consider what we're doing is we're saving the state of the processor to the stack. Before we just pushed all the registers onto the stack and called it good. All the registers onto the stack. So the stack that we were dealing with was, before in the ISR's file, was the IRQ mode stack. All the registers were regular registers unless they were banked. If they were banked, we got the IRQ mode versions of those registers. When we were handling an interrupt before, we didn't worry about the SVC mode link register because we never had to deal with the SVC mode link register, simply because we'd interrupt. That guy would be saved because we never access him in IRQ mode. We'd handle the interrupt and return from handling the interrupt. The link register would be restored because of the fact that we never touched it. Well, if an interrupt leads to a context switch, what we could end up potentially with is the following. We could have the process that gets interrupted could get swapped out. And then the process we swap in will eventually start to execute. When it executes, it will execute in SVC mode. When it calls a function, it'll overwrite the link register in SVC mode. So that gives us a path whereby the link register in SVC mode gets whacked. We didn't need to deal with it before because it wasn't possible for us to whack the SVC mode link register. But because of the fact that handling an interrupt could lead to a context switch, the SVC mode link register could get whacked. So what we're doing is taking the time to save the SVC mode link register while we were in SVC mode. So we push the SVC mode link register onto the SVC mode stack, and then we move the stack pointer into R0. Again, this is the SVC mode stack pointer into R0. Okay? We're moving it into R0 because R0 is not banked. R0 is the same register in SVC mode and in IRQ mode. So we're just copying this guy into a register that's not going to change out from underneath us when we change back. So this is how we keep track of, or how we gain access to our SVC mode stack. Okay, now in 5 we change back to IRQ mode. So just by doing this AND operation with FE and writing that to the control bits of the CPSR. So now we're back in IRQ mode. The thing to remember, SP is now IRQ SP, LR is now IRQ LR, and R0 is still the same R0. It has a copy of the top of the pointer to the top of the SVC mode stack. Okay. Now we push all our registers. We are pushing to the R0 stack. Note this is not SP. We're not pushing onto a stack per se, but we are pushing it onto the region of memory that is the SVC mode stack. Okay? So R0 and the SVC mode SP before this instruction point to the same spot. As soon as we do this, STMFD R0 bang, all those registers, we copy all those registers onto the stack. We leave the SVC mode stack pointer pointing at where it was, because none of this accesses the SVC mode stack pointer. We push all of the SVC mode, or we push all of these registers onto the stack. We move R0 in response due to that bang. So R0 is now pointing at the last register I pushed. Which register is the last one that I push? I have a disagreement. R2 or R15? R2. Okay? The reason why is because when you're doing an STMFD, it pushes, it doesn't necessarily follow the order in which you write the registers in the instruction. It says that the lowest numbered register in this group gets pushed at the lowest address. Okay? The lowest address, you remember stacks grow from high addresses to low addresses? So R15 is the highest numbered one, R2 is the lowest numbered one, and the lowest address is the one that's going to be on the diagram closer to the ceiling. Okay? So, and because they're growing from low addresses to high addresses, the R0 will end up pointing at R2. Okay? We push most all of the registers. Note that we omit R13, and we omit R0 and R1. Okay? Why don't we push R0 and R1? Well, if you recall, what we're doing is we're saving the interrupted process's state with these statements here. R0 and R1 have been overwritten from the values that they had when the process was running prior to it being interrupted. We overwrote those in here so that we could have some room to work with in order to save the state. We kept the processes of copies of R0 and R1 on the IRQ stack. Note, this is being pushed onto the SVC stack of the process. So we've got over here in the IRQ stack, R0 and R1 pushed on the old values that the process had. We're pushing R2 through R12, R14, and R15. Again, we're in IRQ mode, so this is the IRQ mode link register here. We're pushing all those guys onto the IRQ or onto the R0 stack, quote unquote. So this is the region in memory that is the SVC mode stack. We need to now complete the saving of all those registers by copying over the saved R0 and R1 from our interrupted process and put it over here onto this stack, collecting it with these guys. Okay? Why don't we push R13? I'll tell you about that in a minute. Okay. So 7 and 8, all that they're doing is popping. So this guy is a pop. It pops from the stack pointer, adding 4 after I'm done to the stack pointer, and I put the result of the memory read into R1. So if you remember, I pushed the value of R0 and I pushed the value of R1 when I first got into here, so that I could overwrite the contents of the R0 register and the R1 register. Now what I'm going to do is copy them off of the IRQ stack where I had them and put them on the SVC stack in collection with the rest of the registers. So I'm using the R1 register and I'm popping the value of R1 that was saved off of the IRQ mode stack, pushing it onto the R0 stack. So that's what this store instruction is doing. So I'm just pushing the contents that I just popped off of the IRQ mode stack, and I'm pushing that onto the R0 stack, which is the region of memory corresponding to the process's SVC stack. Okay, pop R1, that's 7. You look at this code, LDR R1 SP4. Okay, we'll look at 8. Curiously enough, 8 looks just the same. But what this is doing, we're using the register R1, and we're popping from the IRQ stack. We pushed R1's old value onto the IRQ stack. We pushed R0's old value onto the IRQ stack. What we're doing here on 8 is we're popping the value that R0 used to have in it, and we're putting it into the R1 register, and we're pushing that old R0 content onto the R0 stack. So just because those two instructions look identical to the previous instructions, it's the value that was pushed onto the IRQ stack that's important. It's the old R0 value. 7 grabs the old R1 value and copies it over. 8 grabs the old R0 value and copies it over. Okay? So these two guys just take R1 and R0 and put them onto the SVC stack. So now sitting on the SVC stack, R0 is now pointing, the R0 register here is now pointing to the value of the processes, the interrupted processes R0. So it's got R0, R1, R2, R12, and R14, and R15. All those registers are now saved on the process's SVC stack. Also of note is that the process's SVC stack pointer does not point at the top of the process's SVC stack anymore, because we've been using R0 to point to the top of the process's SVC stack. So the SVC stack pointer register in SVC mode, the SP in SVC mode, is pointing somewhere down here in the stack. All the registers are above it, and R0 is pointing to the top of it. So if I changed to SVC mode and did a push, I'd overwrite some of the process's state. So now I've got to worry about this. Okay. The other thing is, after we've popped the old value of R0 and the old value of R1 off of the IRQ mode stack, the IRQ mode stack looks just like it did when we first got interrupted. Okay? It's empty. So we used it as a temporary location. We used it to hold values for R0 and R1. We've now popped those guys off and copied them over to the other location where we're holding R0 and R1. The IRQ mode stack is back at 0. It's back at wherever it started from. So we've cleaned it up. And that's a good thing. Remember how we don't want to leave the IRQ mode stack in a state that's weird, because another process, after we swap ourselves out, may need it, and it will need it to be at the nominal initial value. Okay. So basically, I asked you in Lab 6 to draw what the quote-unquote R0 stack looks like. I just told you what it looks like. I just didn't draw it. So when you want to answer that question, go back and rewind and read the lecture. Okay, next. So we've pushed all the registers. If you remember back to the CS code, so we've pushed all the registers. We've pushed all the registers. Now what we're going to do is save the process's CPSR. One of the things, Jonathan, are you trying to get my attention? Okay. Good stretch. All right, good. One of the things that the processor does, the ARM core does when it detects an interrupt, it not only changes the mode of the processor, but it also copies the current process's CPSR value, and it puts it into the mode that we enter, into that mode's SPSR register. So the SPSR is a banked register. CPSR is not a banked register. SPSR stands for Saved Program Status Register. So in 9, what we do is we take the IRQ mode SPSR and copy that into R1, and then we push R1 onto the R0 stack. So after all the registers have been pushed onto the stack, we now push the interrupted process's CPSR and put that onto the stack. 10, we store the stack pointer at the top of the R0 stack. Which stack pointer is this? The IRQ mode stack pointer. What does it point to? It points to the same place that it pointed to when we first started this whole process. Remember, we pushed R0 and R1 onto it, then we popped them back off. So this is just, we need to keep track of where is the IRQ mode stack pointer pointing. Okay? This guy is at the top of the stack. So we put him at the top of the R0 stack. So we save him onto the process's SVC mode stack pointed to by R0. Okay. The reason why we're doing that is because we're going to overwrite the IRQ mode stack pointer register's contents. We're going to change the IRQ mode stack pointer to point at the process's local stack. But if this process gets swapped out, we need to remember what is the original IRQ mode stack pointer so that when another process comes in, it has a separate IRQ mode stack that it can access. So we are pushing the IRQ mode stack pointer onto the process's local stack so that we can save it for later and restore it. Okay. Now what we're doing is we're moving R0 into SP. So if you remember, R0 points to the SVC mode stack of the process that got interrupted. We've loaded all the registers and the CPSR and a pointer to the IRQ mode stack onto that stack. And now we're going to move R0 into SP. So that points the IRQ mode stack pointer at the process's local stack. Now remember, the process's SVC stack pointer is still pointing somewhere. We've got all the state on top of there, and it's pointing down below. So we've got the IRQ mode stack pointer now pointing at the top of the process's local stack. At the top of the process's local stack is a pointer to the original IRQ mode stack. All right. Now we're going to change the SVC mode. So we change the SVC mode, then we move R0 into SP. So if you note, move SP, R0 was the same instruction that we had in 11. So what we did is we pointed the IRQ mode stack pointer to the top of that R0 stack, the process's local stack with all the saved state on it. And now we change the SVC mode, and we move this SVC mode stack pointer to point to the same spot. Okay? So now we have R0 pointing at the top of the process's local stack with all the state saved on it. We have the SVC mode stack pointer pointing there. We have the IRQ mode stack pointer pointing there. Everybody's pointing there. At that location is a pointer to the top of the IRQ mode stack, which is a whole different stack. Okay. So we're changing this. We have the SVC mode stack pointer pointing there, IRQ mode stack pointer pointing here. What that move to R0 does is it moves this guy to point up to there. Okay, step 13 just changes back to IRQ mode. Step 14 is a branch and link to go handle the interrupt. So step 13 and 14 are just right there. So all that these guys do, change back to IRQ mode, and now go and handle the interrupt by branching to that code that accesses the bit. Okay? So where are things standing right now? We've got the stack pointer for the IRQ. So we are handling the interrupt in IRQ mode. The IRQ mode stack pointer is pointing at the process's local stack. At the top of the process's local stack is a pointer to the original IRQ mode stack. So what this allows us to do is it allows us to, when we handle an interrupt, that's going to, we're still going to have functions and code that add to the context of the process that got interrupted. So it's going to call some functions and maybe have local variables. that can't be shared between processes, so that still forms part of the context of the process. So we have to make sure that when we handle an interrupt, the stack that we're accessing at this point has to be the process's local stack, okay? And we're also making sure that we handle it while the mode of the processor is IRQ mode. So, easy as pie. Got it? This is not trivial stuff. I recognize that. This much I can guarantee. I'm not going to test you on this. Yeah, you won't have to rewrite the IRQ, the ISR's file, and handle all this mode switching then.
So, like, just to clarify, so when we're in an interrupt in IRQ mode, but we're working on top of the SVC stack?
Okay, so when you're in an interrupt, by default, we have the IRQ mode stack pointer pointing at some other location, and we have the processor in IRQ mode. So what we've been doing to date is we've handled all the interrupts while the processor's in IRQ mode, and when it accesses the stack, it's accessing a special separate stack. Okay? Because of the fact we're now introducing context switching, we're making the interrupts get handled by pointing the IRQ mode stack pointer back to the process's local stack. So you remember that question on the exam that says, why do we have two stack pointer registers? Well, it's to improve security. Well, we're pulling the pants down on that. Okay? We're not going to allow us to have that added security because we're going to force the interrupts to get handled by having the IRQ mode stack pointer point at the process's local stack, because unfortunately what that does is that we have context associated with a process when we handle an interrupt, and if that context leads to execution of an interrupt leads to a context switch, we can't have all that state that we build on the way to where we call CS be in a shared location that will then be referenced by another process, because it'll mess that other process up and it'll mess the process we're swapping out up. So we have to have the process, and the only other solution would be to have every process have its own separate IRQ stack, which we didn't want to go through and do. Okay. So yes, we are handling an interrupt, and yes, we are using the process's local stack, which is its SVC stack, but pointed to by the IRQ mode stack pointer. Okay? We good? Okay. So, control flow for preemption. This just summarizes stuff that I've already been talking about. You have the VIC that senses the need to interrupt the processor. So some interrupt source like the timer or some external source tells the VIC, hey, I need to interrupt. And then the VIC pulls the IRQ line of the core. The IRQ line fetches from address 0x18. That's an instruction that says jump to whatever is at address 38. That address is IRQ interrupt ISR, which is the name, the label associated with all that assembly code we just went through. Okay, that messes with the stacks. Then you jump to IRQ interrupt handler. That jumps to PIT, and that jumps to some other stuff that we're going to talk about next, and that'll jump to CS sometimes. Okay, so the CS is what will do the context switch. Okay. Okay. Now, because of the fact that the processor is in IRQ mode, from the time that we call IRQ interrupt ISR, and when we get down to CS, so all this control flow that's in there, the SVC mode stack pointer doesn't ever change. Even though we may push stuff onto the stack, we may declare local variables, we may save local registers, all of that gets pushed onto the IRQ stack. So by the time that CS gets called, we may have a bunch of stuff pushed onto the stack, and the IRQ mode stack pointer is pointing way up here. The SVC mode stack pointer, if you recall, we pointed it, by the time that we left IRQ interrupt ISR in order to go to IRQ interrupt handler, both of the stack pointers were pointing at the same spot on the stack, on the SVC mode stack of the process. From the time that we go from here till we get to the CS, we may push more stuff onto the IRQ, onto the stack pointed to by the IRQ stack pointer. But the SVC mode stack pointer still stays pointing where it's at. Okay? The trick is, what is it pointing at? It's pointing at a pointer to the original IRQ stack. That is why we pushed a pointer to self or pointer to the top of the stack onto the stack inside the context switch code. because when we swap a process out that is being swapped out preemptively, we have to restore the IRQ mode stack pointer to the original IRQ stack. Okay? So it'll grab the SVC mode stack pointer, which points it to the IRQ stack, and move that into the IRQ mode stack pointer. If we start in SVC mode, all that does is just move the stack pointer over the top of itself with itself. But in preemption, when we're coming from IRQ mode, what that does is it restores the IRQ mode stack pointer to point to the original IRQ stack instead of the process's local stack. Okay, and then as the context switch code restores the state of the new process, it may alter the IRQ mode stack pointer to point at whatever the process's stack is, depending on what the mode of the process that we're swapping in is. If that mode of the process we're swapping in if that process was swapped out preemptively, when we fetch and restore its CPSR value, that'll cause us to switch to IRQ mode, and when we monkey around with the IRQ mode stack pointer, that'll point the stack pointer to that process's saved stack, and that'll update the IRQ mode stack pointer register. It's a mess. You're going to have to trace through it, and then watch the lecture, and then trace it again, and then watch the lecture again, and maybe it'll help. And come talk to me for a bunch of times. Anyway, so this is the other half of the ISRs file. So after the branch to the VIC code, which handles the interrupt, we eventually work our way back here. When PIT returns and CS returns and all that returns, we return back to this code. I'm not going to go through this in great detail because all that it does is does what we just did, but backwards. Okay? So it still saves the R0 and R1, but it has to do to get some working space. But basically, it all boils down to pop all the registers off the stack and set the stack pointers to where they should be. Okay? So you are going to need to draw a stack frame of this whole nasty business in Lab 6. You're going to need to draw a stack frame in Lab 5 for using the old ISRs file. So don't get confused about this ISRs file and the old ISRs file. So Lab 5, you don't have to deal with this. Lab 6, you have to deal with this. Okay? Questions about this nasty assembly code? Anybody still awake? Anybody wish they weren't? Okay. Now, all that stuff is the painful part. This is the cool part. Okay? Now we're going to talk about how to create processes. Okay? So this is the basic guts of what's going to be the fundamental aspect of our operating system that we're writing. Okay? We have to be able to create processes. We have to be able to switch between them. We've talked about switching between them and what's the context of the process. Now we're going to switch back up to, more sane stuff, a little bit higher level code, which is, C. That's about as high as we get. But we're going to talk about process creation and how to schedule processes. So on this set of notes, we're going to talk about creating processes, and we're going to define a rudimentary scheduler, which is the fundamental aspect of an operating system. So if you remember, I talked about processes before, and I said that a process has a lifetime, and you model that as a state machine. And the states of the state machine say, how does the process spend its time? So a process in our initial operating system, you are initially idle, and then eventually you become ready, and then eventually after that, hopefully you become running, and then you go back to ready. So these are the states that a single process can be in. You can have multiple processes running. Each of them can be in any of these states. However, what we have to realize is that because we only have one processor, only one process at a time can be running. You can have multiple processes that are ready, multiple processes that are idle, but only one at a time can be ready, or can be running. Okay? Okay. What is the idle state? That's used for a process that may exist in memory, but is not beneficially instantiated or initialized. So if we just have like a data structure that has a whole bunch of task structures allocated, we're going to say that those guys are idle tasks because they're not doing anything. We're not actually going to try to allow them to compete for the processor. So really the only two states that matter are ready and running. So we're going to define a type def. That is an So we'll say these are the various states that a process can be in: idle, ready, and running. We'll define idle as one. Okay. We're going to type def that enum to be process state. So a process can be in the state idle, ready, or running. We're going to define a type def called context. Context is a pointer to an unsigned integer. This is the type that we'll use for pointing to the context of a process. So if you remember, we put all the bunch of stuff on the stack, and then we point a pointer to the top of that stack. The data type of that pointer is going to be context, and it's just a pointer to an unsigned integer. We have a data structure that we will use to hold the state of a process. Okay? So this data structure will expand over the course of the semester, but for right now, we're just going to say we've got a type def struct, process struct. It has two fields, a field of type context in caps that's named context in lowercase letters. In caps, process state in lowercase state. Okay, so two fields, context and state. Okay, the name of that, we're type defing that struct to be process. So we've got a process structure. Every process has a state and a context. Okay, if the process is running, the context pointer isn't valid because the context of a running process is the contents of the registers. Okay, a ready process has been swapped out. Its context pointer points to the location in memory where its saved context is located. Okay. So this is a pointer that's available to hold our or to point to where our context is held when we get swapped out. Okay. Okay. We keep track of a process with that data structure. We have to keep track of all the processes that are in our system. We use another data structure to track all the processes. We have an entry point associated with each process. So a process runs code. Where does it start running its code? That's called the entry point of the process. We use as an entry point, guess what? The address of an assembly instruction, which is the first instruction corresponding to that process. What is the first instruction? Well, normally under a desktop operating system, you would have as different programs that you run, and you say // I want to run this program, something like that, and then it will load that executable file, create a process, copy the contents of the executable file into the appropriate locations into memory, and jump to the entry point. With our operating system, we are not going to handle multiple executable files. We're going to compile in all of our processes as part of the same program. So effectively, we're doing threading. Okay? So every process has an entry point which corresponds to a function. And we're going to effectively jump to that function and let that function execute. And that function will be executing concurrently with other functions in the system. And those will be our processes. So the entry point is just a function, and it gets invoked by our operating system. Okay. So all the entry points have the same prototype. And this is the prototype, and we're going to use as the entry point a pointer to a function. Okay, so we're type def void star process function int p. So what this says is process function is the name of the data type that I'm going to declare for the entry point of the process. The data type is a pointer to a function. We tell that by the star in these two parentheses initially. It is a pointer to a function that returns void and takes a single integer parameter named p. Okay? So entry points are functions that take a single integer parameter and return nothing. How do we keep track of all the processes that have been created? We use a queue or a FIFO. You implemented a FIFO before? You ever seen a FIFO? Guess what? Blow the dust off of Lab 0. You're going to have to implement a FIFO to hold processes instead of integers. Now you know why I made you write a FIFO. Okay. Type def process star FIFO data. So what we're going to do is we're going to modify our Lab 0 FIFO so that it will hold processes instead of int. We're going to call it a ready queue, which is a queue or a FIFO, a linked list of processes that are ready to run. We'll have a pointer to a process that is the running process. Okay? So we'll type def process star FIFO data. So if you remember, we abstracted the data element of our FIFO by calling it FIFO data, and we had a type def unsigned int or type def int FIFO data. Here what we're going to do is type def process star FIFO data, so that'll let us use a pointer to a process as the data that's included in our FIFO. Okay, we will have static process FIFO star ready queue. So this declares a pointer called ready queue of type process FIFO. What's process FIFO? we're going to, we have our FIFO, we can type def a FIFO to of type, a FIFO that holds processes is a process FIFO. So ReadyQ is a FIFO that holds processes. And all that's just your lab 0 code, modified slightly. Then we declare static volatile process. There we go. Okay. Static volatile process star process running. So this is a pointer to the currently running process. We only have one of them, so we only need one pointer to one running process. We declare it static because we only want to access it in this current file. We declare it process star because that's its data type. We declare it volatile because the value associated with process running, the address that it points to, could change asynchronously or outside of the normal flow of the program. We want to tell the compiler, don't assume anything when you reference process running. So we use the keyword volatile to turn off compiler optimizations associated with this variable. So that way, if we reference it inside our program multiple times, it'll issue a load from that memory location each time it references that memory location. It will not just hold that address in a register and reference the contents of the register. It will do a load each time. And that's because the value of process running could be set by an interrupt service routine. So anytime you have variables that are shared between your main code and your interrupt service routine, use volatile. Okay. We declare a prototype for context switch. We've seen that a bunch of times. We have a prototype for a process creation and scheduler. So we're going to implement this function called proc create, which takes a process function called f, an integer parameter, and a pointer to a stack. So this is how we're going to create a process. We're going to tell the code that's going to create that process the name of the function we're going to use for the entry point of the process. This is the integer parameter that we will pass to that function as it gets called, or as we invoke the entry point. And then every process gets its own stack. So we're going to pass it a pointer to a memory location, which is not shared by any other process. That'll be that process's stack. This is a culmination of the lecture slides on these notes, because proc creates the nasty one. Well, it's not nasty, but it's the most fun. We also have a function called start scheduler. Start scheduler, we're going to set up a bunch of stuff for our operating system, and we fire the whole thing off by calling start scheduler. So we'll create a bunch of processes and call start scheduler. That'll start to run our processes. This is the implementation of our scheduler called schedule next process. So this is a function that we swap the currently running process out, and we take the next process that's waiting and swap it in. Okay? You can call schedule next process from an interrupt service routine, or you can call it straight from a process. And if you call it from the ISR, that's preemption. If you call it from the process itself, that's a cooperative swap out. Okay, so next time we're going to dig into this code. We'll look at schedule next process, start scheduler, and proc create, and then you will have everything you need to do Lab 6. Okay, type def is used for creating an alias for a data type. Pound define just associates one symbol with another, does a text search and replace. So you can use pound define in some way like you use a type def. But the compiler evaluates a type def, the preprocessor evaluates a pound define. Okay, you can use pound define for replacing all kinds of stuff. You can't use a type def to change max num to 3. You can only use type def to define types. You can use pound define to model all kinds of substitutions. But again, it helps that you're using a type def that gets evaluated by the compiler at compile time as opposed to the preprocessor when the preprocessor runs, because you get much more cryptic error messages if you do it wrong with the preprocessor. Okay.
You said that not to use the do while in bound define in macro in the lecture.
Not to use what?
Do while for.
Okay. I said that it's usually good practice when in general you're defining macros to enclose them in a do while loop. But for this assignment, you're going to find that that's not necessarily applicable.
And do we use a bound to use as a string, like if I take.
Okay, so I discussed in class the stringization